If you haven't used Voxelmap yet, or you don't know what it is, well, Voxelmap is a Python package that uses NumPy arrays and mathematics to make, develop, or load three-dimensional models. At least rudimentary three-dimensional models in terms of loading, not so much on the making now. Voxel started as a very simple project, which did less than that, of course. We started by using three-dimensional or higher-order arrays to represent voxel models in 3 dimensions. And now it has expanded, as I mentioned, to some more interesting features, such as mesh creation and the like. Okay, so without further ado, actually, I just wanted to give some scope of this video. I will be showing you the new methods which are new in versions Voxelmap 2.0 and beyond. I will also be placing a link of the former video of Voxelmap so that you can see the older features, and if you want to become a little bit better at it or more proficient on Voxelmap, I recommend you watch it. For now, we'll just show you the newer implementations and features of these newer versions. So for that, I will start also using creating a virtual environment for our package. I believe now it should be the more prudent thing to do, really, is to run your project on a virtual environment, at least your Voxelmap project. Okay. For that, we'll go to our desktop. We'll create a project file on our desktop called project. Okay, and now I will be going into the project, and if you what we'll be doing is creating that virtual environment by typing virtualenv vmp. It's the name of our virtual environment folder or repository. If you haven't already realized, I am just following the instructions of the README of the Voxelmap repository here. So the first one was virtual environment vmp. We'll be opening a Visual Studio Code to run on the whole project folder, which we are creating. Okay, and now we will be activating that virtual environment by typing source then activate. So now we are in our virtual environment. Okay, now because we are in a virtual environment, we can install Voxelmap in that environment. Type install. Upgrade flag here to just making sure that we're downloading the more updated version of Voxelmap. And so you can see now that it's going through the whole process of downloading all the packages, dependencies needed for Voxelmap, and Voxelmap as well, of course. Now we are even implementing some packages that use OpenGL graphics, Pygame, and so on, and the like. I think it even has pandas package, but I digress. So what I will do right now is I will just pause the video, and I will, because this will take some decent amount of time, right? Okay, I believe this should be about finished now. The whole installation of Voxelmap is just taking some time. As I mentioned, I'm just going to pause it again. Okay, now that it's done, it's finished. It should be installed now. So a good way to see that it's installed, right, is just go to Python and then just type import Voxelmap and see that we don't get any error. And then we do not get any error. Okay, so it should be installed now. We just exit Python here. Whoops. Okay. And now what we'll do is we'll be running some examples here that are also, you can also find in the Voxelmap repository. You are able to find, you can find those inside this the extra directory in the Voxelmap repository. So that's what we'll do. Go to extra, we'll be downloading them, the examples on a need to use basis. Okay, so we'll start with the dog Python script. And so for the dog Python script, we can just click on it, copy paste the code, or even go to the raw site of the code. and then create a new file and everything, but I'll just make it simpler and just because I'm using the terminal, I'll just do wget on that script and the address, copy paste the address, and then that should be just like that. We have the Python script in our local directory now that we just created, our project directory. Okay, easy as that. So you can see that code script. We are importing the Voxelmap package. We are defining a sparse array containing all the voxel information, and this sparse array is defined as voxel dog. This is a NumPy array. It's a sparse array because there's lots of zeros which are not used. The only thing that our algorithm, not our algorithm, but our package recognizes as voxels are non-zero integers, right? And so you can see some non-zero integers there. And of course, then after doing that, it will basically draw the integers because this is a three-dimensional array, right? So it will just draw this into a matplot library model. Of course, this is what you need to do to pass the three-dimensional array to Voxelmap. You need to pass it as a variable by integrating it to the model class of Voxelmap. Voxelmap is abbreviated as VXM on top, right? So it's voxelmap.model, and then Voxelmap, which is that array, transformed array. And then here, just the alpha is just like the coloring map that we're using, the transparency or opacity of the color map, and then we draw, right? So we'll be running that code. This is nothing. There's nothing new here really, but just showing you what the code, explain to you what the code does. So it just draws a little presentation of a dog. Okay. It's semi-transparent because we set up an opacity of 90%. Now there's nothing new on this. Our new feature, however, which builds on top of the previous version, is the loading and saving capabilities of the model. And so we can save the model into a JSON file by just typing model.save with the save method, right? And we can name it dog.json. It will save it as a .json file. It will basically save the array information as a JSON file. And a very efficient one at that. So we rerun the code, we comment out the drawing feature, and you can see that now it's created a new variable called dog.json. We can do something, what we can do? We can put this JSON file information in JSON lint so that you can see it in a little nicer way what it has, the contents of the file, of the newly created file. So you can see that it has hash blocks key and value. And this is just if you want to assign specific colors to the non-zero integers which are considered to be voxels in the plotted model. A size is basically the dimensions of the third order array, length, width, and height, length, width, and depth. And coordinates are the coordinates for the non-zero integers in that array. And of course, val is just, as you may have guessed, corresponding values of those integers pertaining to the coordinate, where they are in the coordinate space. Okay. And so with that information, now we have that JSON file. This has actually been a suggestion by one of our YouTube viewers on a former video, on the first, on a former video of, not former video, but an older video of Voxelmap, which they suggested, oh, maybe it would be good if we could just like, save the model and use it somewhere else, right? So I just implemented that feature yesterday, I believe. Okay, so now we have that dog.json file. We can create a new Python file and load it there, right? So touch, we'll just create a new Python script called new.py. You can see that it's empty, right? We'll need to add some stuff to it. We will import Voxelmap as VM. And now to place all that information from the JSON file in a new model, what we need to do always is we need to make a blank model first. Okay, so we make a blank model by just calling voxelmap.model and not typing anything here, just parentheses. And if we want to load the model, the JSON, all that .json information in the blank model, we just type model.load, and then of course the name of the file, doc.json, and it is as simple as that. If we want to draw the model, then we can just do that. The loaded model, which is integrated right to the model variable, then we just type model.draw, and it will do that, just that. It will draw the dog again in this new file. We save it, we run it, and then we, here it is. Here it is again, our cute little dog. Okay. Now I'll show you another example which does color assignments for the specific integers in three-dimensional arrays. Okay, and that example is also housed in within this extra directory in Voxelmap, right? It's called, I believe, island.py. Okay. And we will be basically grabbing it also using the wget command in the terminal. Okay. And that should bring us, that should basically grab that code from the internet and put it in our computer. Okay, so you can see that this file now, we are also importing Voxelmap as VXM here, not VN. We are basically defining an array which represents the voxel information from of the object we want to draw. And of course, as I mentioned before, Voxelmap only draws the non-zero entries and considers them as voxels. And if we want to go a step further, right, we can define a specific color and alpha transparency to the voxels, to the integers in these three-dimensional arrays. So the keys are of course the integer values for which we want to define a color, which is the value, the first value in this dictionary, right, in hexadecimal form, hexanumerical form, and the second value, the second entry of the values from the dictionary are the relative transparency or relative opacity actually. So we'll change the relative opacity of two thieves as 0.5, so half as transparent. And of course, if you want to make these color assignments, you have to define them within this constructor variable of the model class, which is called .hashblock. So you have to always define, whichever name you want to give the variable. Model could be dog, island. Then you have to follow. It has to follow by model or island or dog .hashblocks. Okay, just making sure that you understand that. And of course, if we want to use the customized voxel coloring scheme for the drawing, you basically have to define voxels, write voxels as the coloring scheme here. Otherwise, it will default as the nuclear coloring gradient, which does not, define. Well, I'll show you what I mean. Okay, so we'll just run this code again. We'll run this, not this code again. We'll run this code first without the loading and saving feature. You'll see that it will give us an island. Now this island, I actually drew it using voxel. Okay, and we have also an interesting utility which uses a voxel class within this Voxelmap package, right? Which basically can transform a voxel model to an array. Okay, so you can also check that on your spare time. I will just not show it in this video because I believe I showed it on a previous one. Okay, that you can watch. So that's basically what it does, right? You just, of course, I didn't save this file when I redefined the transparencies for the integers 2 and 3. So if I save it and rerun again, some of the voxels will be semi-transparent. You see those twos, I guess the integers 2 and 3, they belong to the voxels that are green and brown. As you can see now that they are semi-transparent. Like a glass, it seems even. Right? Okay. Now, of course, what we can do here with our new feature on Voxelmap versions 2 and beyond, so we can save it. Model save, and we can save it as, I guess, island.json or any other name you want. json. Okay. So we rerun with commenting out the drawing feature, and now that creates a new island.json file. Okay. We can place it in JSON length to see how it looks, how pretty it is. How pretty it is. Okay. And you can see that the first key or fetch entry to the hash map or dictionary is hash blocks. So basically, it holds all the color assignments, color and transparencies for integers 1 to 5. And then, of course, it follows by what I mentioned in the previous file, right? So the coordinates, the dimensions of the array, and the values for the non-zero integer values. Okay. And so we can go back to our code and to our new .py script. And so instead of loading the dog, we can load the island.json file. Okay. And we just, if we just like do not assign any argument to the draw method, we can just run it again. Not run it again, sorry. We can run the new .py script, and you'll see that we get an island, but we don't get it with a custom color scheme, right? We have here, it defaults to the nuclear coloring scheme, which uses a cool map gradient. You can also change the color map if you would like. I believe it's on my other video as well, and if it is not there, it's under the documentation. But it uses a coloring scheme which doesn't really work on it's basically the coloring scheme which you use to color the dog, right? But if you want to use the colors that you assigned to the model, you just type voxels as the argument or the entry, the input call to the draw method, and then you rerun Python, and you should get the voxel model colored with the voxel color assignments from the JSON file, right? From this file. Basically, it integrates this. It uses this to draw the model with Matplotlib library. Right? So these are the features. This is the new feature on this Voxelmap. This newer Voxelmap versions. The other new feature, which I wanted to show you, it's a little bit more complicated. It's called an ImageMesh method, which uses the image class of Voxelmap, which is a method from the image class of Voxelmap. And so for that method, I will show you basically, we'll be downloading also some files. We'll be downloading the land.py file, not island, but land, which is also on that extra repository. Okay, so we'll be downloading that file. Go wget. Okay, we wget the land Python script. We'll be also wgetting or extracting a PNG file in also this extra directory. This is just a drawing. If you want to see how it looks, it's basically just a very tiny drawing of a topography-like type of representation of two mountains, right? And so because I used the wget on those, it's on my repository, not my repository, sorry, on my project folder. Okay, you can see that that's the land the Python script for land is there, and also the .png, which will be operating, is here as well. And so ImageMesh, right? This is the new method, new development on our Voxelmap versions 2 and beyond. And what ImageMesh does is something a little bit more complicated than what I showed you before. Something a little bit more complex even than a three-dimensional mapping from an image. What ImageMesh does is it takes an image, it transforms it, well, it transforms into a relative intensity matrix, which is basically just how dark each of the pixels of the image should be in grayscale format. And then after doing that, after doing this calculation, it creates a point cloud based on a relative depth which is dependent on that pixel intensity. With that point cloud, you also what we do is we triangulate the external points on the point cloud to create a mesh-like three-dimensional object. And of course, we save that object afterwards as a wavefront file. That's basically what it does. Now, the beauty of this algorithm is that typically, so it uses something that is called three-dimensional convex hull. A three-dimensional convex hull will typically not give you a well-resolved triangulated mesh by itself. So I guess that my intellectual contribution here, or what is new, what I have created, is really a segmented algorithm, just basically doing a segmentation above a three-dimensional convex hull. Okay. So the method for ImageMesh, which you may actually find somewhere on my website or Voxelmap, the Voxelmap website, is, if you want to be more specific, it's a segmented or sectorized three-dimensional convex hull of images. Okay. I will not elaborate so much on that on the explanation. I would rather here just wanted to showcase the features that you would, something what you may find new in these versions. If you'd like, you can do so in your spare time and just like, you know, look at the documentation that I may have available. Okay. So let's start with this code. Okay. So what we do here is very simple. We import Voxelmap as VXM. We call on the image class and make a variable image, basically, which loads the land.png file. Then we need this line number 7. We make the relative intensity matrix, and then of course we then apply ImageMesh to that whole thing. Okay. MeshView, then basically it's a method which draws the ImageMesh created object using OpenGL graphics. It just makes the rendering much more efficient. Okay, so I will be running then this land.py script. And so you can see here, this is the result of line number 11. After, you know, ImageMesh is transforms the .png file and everything. So we went literally we went from this. Oh, sorry. Where was it? Yeah. From that image to making this three-dimensional mesh-like representation. Okay. And of course, ImageMesh has other arguments which you may customize and everything. I will be showing you some of these by example. Okay, what they really mean. You can look at the documentation as well, but just I guess it makes it simple if I just make some changes here and there so you can understand it better. Okay, so land.obj is just the name of the wavefront file you want to give to the file that ImageMesh creates when it does this triangulation algorithm. Okay, so in this case we are just naming it land.obj. You can name it something else. You can name it something else if you'd like. It could be land1 even. It doesn't have I'll just leave it as land. I can just recreate it, and it will make a land1 file, right? So just delete it, delete the created obj file. We run the Python script again, and you can see it just creates a file called. Oh, sorry, I didn't save it. Okay, so let me just delete obj again. Okay, Python land, and it will just create a file called land1.obj. Okay. And now the second argument you see here, it's a length scale of the number of sectors that you want to do three-dimensional convex hull in of the image. Right. To explain that in a nicer way, I guess I can just do that by example. If I change the length scale, a length scale of 12 will actually split the image in 144 sectors to do three-dimensional convex hull on each of those. Right, and that's because it's 12 by 12, basically. Just the image, all images are 2 dimensions. And we can change that number to 1. So if we just want to do three-dimensional convex hull, just using on the whole image without splitting it into little pieces, right? We change that number to 1, that length scale to 1, and then we run the algorithm again. Okay, and now you can see that it gives us a less, quote-unquote, less resolved mesh-like representation of the image. Right here, you don't see 2 mountains. You just see one, and not very well resolved. And the reason why you see that is because when we do not sectorize the image or cut it into little pieces to apply convex hull, it is very akin to just placing a sheet of paper on top of a point cloud object or representation. If you place a sheet, then you will not be looking at all the very detailed structure of the whole point cloud. Right. So this is basically why there's no separation between the two mountains of that topography-like image. If we make it a little bit, split it, cut the image into more pieces, maybe 4 by 4 would be a total of 16 sectors, then you'll see that you start seeing more resolution, right? You know, the algorithm can now differentiate or draw 2 mountains instead of just like one connected by a mesh grid, by a mesh triangulated type of object. Okay. And of course, if we can go up to 14 even, and we'll just cut the image into more little pieces, and we'll increase the resolution. Right. So you can see that it now makes it even a little bit more resolved. And so I guess that's the beauty, not the beauty, but that's this insight, the additional insight to the three-dimensional convex hull algorithm and the intellectual contribution that I'm making. This is why it's the creation here that I've made is just integrating this sector algorithm, the segmentation algorithm, to do above three-dimensional convex hull, so that you can get well-resolved images like that. And in a very efficient way, of course, because we can now use OpenGL graphics. And I believe that triangulated meshes, they are the norm for three-dimensional rendering now. Or they are what's popular, right? Because point callouts are then taken and modeled with triangulated polyhedron-like meshes. Okay. There are some additional options, of course. Here you have also last other entry, 0.52. The input that has a value of 0.52 is the relative depth, and that's used because we do not really know how to represent the depth with this algorithm, depending on how the computer assigns the relative pixel intensity. Right, so that's not something that we have evolved so much. So we have decided to make it an input here. And just to explain that nicely, I guess we can just wget a different image here from also the GitHub repository or GitHub Voxelmap repository. This is land.2png, and this one is a little bit more different, a little different than land1png. Right? You can see that it's actually a higher resolution image, and it has more. It may have different values for the relative pixel intensities, because there are some areas which are darker than land.png. Okay. So if we redraw, basically we go back to our land.py and we integrate land2png, which is this new PNG file, to that Python script. We redraw it, and if we redraw it with that change, you'll see that of course it's running. It's calculating, it's doing more calculations because the image is larger, so it takes a little bit more time. And also the view of the algorithm, the view of the created image is different. Right? As you can see, there's flatter, and this is basically because of that depth issue we have on the image mesh. So we can increase that to maybe 3.5, just increase the relative depth by 7 relative to the other, to the depth which we processed in this run, right? And so we're doing that right now. We changed it from 0.52 relative depth to 3.5. And so when we redraw it, you see a taller image, a taller mountain range, right? So you can now see there are some sections here. You have a well in the center and some more well-resolved sections. Of course, you can increase the segmentation, the number of segments, but I'm not going to do that because it's going to take some more time. Okay. The other algorithm is trace minimum, is something a little bit more complicated. Just minimum number of points in different depth levels to triangulate. It's like a threshold type of thing. You can do some more reading on your I'm not gonna elaborate too much on this because it will extend the video to more of what we would want it to be. Okay, but I just suggest that you leave it as the default value. Here I just change it to 1. Okay, the other algorithm you see here, false, is just a Boolean option to do the plotting, to use the plotting tool on the image mesh method, which I have set it to false here because that plotting tool uses matplotlib, and it's a little slower compared to the OpenGL graphics, which is basically what is used for the MeshView method. But so if you want to, if you just want to see it, I'll just run and set that boolean to true, and so you'll see what I'm talking about. Actually, I think it will be safer if I just run it using the first image, because otherwise it will be way too slow. Okay. So, and of course it's gonna give me a very tall graphic, right? Because I didn't change that setting. So I'll just change it back to 0.52. Okay. Rerun. And yeah, so it was 144 copixel segments, and you can see that the rendering is just slower. It takes some time, more time, and this is because Matplot library, I believe, either uses the CPU or it just doesn't exploit the GPU so well, right? So it takes more time. Whereas if you just set that boolean to false, you create the object, everything with image mesh, but you use the MeshView or OpenGL graphics to do the rendering, then you'll see that it's way faster, right? OpenGL just exploits your graphics GPU card in a so much more efficient way, right? And of course, we have created, as I mentioned, well, I just rerun it and to create a land.obj wavefront file. So that obj wavefront file, which we created with ImageMesh, we can also apply or import it to Blender, which I think that is just a very cool thing. Oops. Blender. Right. Okay. So if we just go to import wavefront and basically the place where we have we're housing the wavefront file, which is here in project inside desktop, and so we load it. Okay, and so now you can see that we've loaded our created image mesh file to Blender. How cool is that? Right, we could take the file, and because it hasn't been like, it's not in the right position, orientation, we can change it. The orientation, we can change also, bring it up, raise it. Can bring it up a little more. Maybe I want to delete that cube, and we bring it up. Yeah, and then we can make more changes. But that's basically that's the new implementation. These are the new implementations, the new methods of Voxelmap. We can also save this model in Blender as a Blender file, and we can save it as also, what do you call it, land.blender, blend, so that we can, you know, load it at any other time. Okay. So these are basically. I'll just close Blender this way. Oops. Yeah, save it. Okay. And so these are basically the main features, the new features of Voxelmap. All right. So I hoped that you liked this video, that you learned something new, or that you are excited to start using Voxelmap. If anything, as I'd like to mention also that if you have any you want to propose or contribute or work on any new enhancements or issues to the Voxelmap package, you're more than welcome to do so. I'm open to new meaningful contributions to this open source as well. And so with that, I'd like to thank you for watching this video. If you like what you're seeing, there's a subscribe button here and also a thumbs up button. All right, thank you.